Yes, there we go. Okay, so a warm welcome to everyone. We'll be taking you through the optimization of a supercritical carbon dioxide power cycle that we did in collaboration with Qfunsoft. Sorry. Yeah, so I'd just like to introduce myself again. I'm Ronnie Wagner, and I will be talking to you about the Flownex side, and then Jean-Louis will be taking over on the Qfunsoft and Ansys Optislang side. I would also like to acknowledge our team's work on this project, Leander Klein and C.F. van der Spijn. So for those who are unfamiliar with what Flownex does, it is a simulation tool to assist you with 1D flow and 2D heat transfer using fundamental physics, which is mass flow, conservation of mass, momentum, and energy, and can also feature a steady state and transient simulation. The results are accurate and reliable, as it is built within an ASME, NQA1, and ISO 9001 environment. And our team of support engineers are always happy to help. So if you need any assistance with a Flownex simulation, you're welcome to reach out. Furthermore, Flownex features a very large library of components and fluids. And on the right, we have a quick simulation of a PEM fuel cell that has, as you can see, a transient temperature and airflow control system with heat transfer, pumps, valves, and custom components. Flownex can also be used with Ansys CFX, Fluent, Mechanical, and Workbench, and supports FMI to complete a ROM builder. Some examples of where Flownex and Ansys have been coupled is the first two is in Fluent, a data center, heat exchanger, and then the third is in Mechanical, which is also a type of heat exchanger that was simulated. So getting to our project, taking you back to basics a bit with the supercritical CO2 Rankine cycle, just a normal Rankine cycle. A pump is used to compress the fluid, which is then heated by a boiler, and the excess energy is extracted by the turbine. As you can see, the cycle operates within the two-phase region, some of it in fluid and some of it in gas. A supercritical cycle operates out of this two-phase region where the fluid is no longer a gas or a liquid. For these capabilities and to simulate a supercritical CO2 cycle, you need specific fluid properties, the ability to simulate in transient and heat transfer components, which are all available in Flownex. And so we simulated this cycle, which is essentially a design cycle at the moment, having the compressor, the preheater, and then the heater, going to the turbine where the power is used to power the compressor, and then the excess energy is used or is the deliverable. The fluid is then cooled using the preheater and then a cooler. As you can see, this cycle operates above the two-phase region and mostly not going into the two-phase region. To optimize this system and have the best outputs that we can get from the system, we would like to use Ansys Optislang to couple quantifiable results to the optimization. What we collaborated with, okay. So the input or the output parameters, what we want from the optimization study is to optimize the power of the turbine, the net power output, and of course the life cycle cost of the system. The elements that we will be looking at was the shaft speed, the diameter and fluid path or pipe lengths of the heat exchanger, the mass flow rate of the water at the cooler, and the mass flow rate of air in the heater. And this is where I will hand over to John Reed to discuss further the Ansys Optislang part.
All right, thanks, Rani. Let me just quickly share my screen as well.
Pleasure. If anyone has any questions about Flownex, you're welcome to pop them in the chat box, or we can discuss them at the end.
Okay. Can everyone see my screen or not yet?
I can see it, yes.
Okay, fantastic. I just want to see it working. Sorry about that. Okay, cool. Okay, yeah, so thanks, Rani, for quickly introducing the Flownex problem that we would like to or did try to optimize through using this Flownex-optiSlang interface. What I'd quickly like to just cover are some of the main features or capabilities that I feel make OptiSlang a unique optimization tool. And these features are also the ones that we predominantly make use of within our study. So the first one I'd quickly like to just run through is the process integration and automation capabilities within OptiSlang. So what you can basically do in OptiSlang is you can do graphical programming, and you can incorporate your solvers into an automated workflow, all the way from solving the model, then downstream doing some sensitivity analysis, optimization, and you can even automate the process all the way up to sending the email, as you can see if you're feeling particularly lazy that day. And of course, to enable these kinds of automated workflows to be generated, there's some in-house and third-party tools that can integrate with OptiSlang. And of course, it can also then integrate with the Workbench parametric system within ANSYS as well. So just speaking of which, just to show you the existing integrations and interfaces between other software and OptiSlang, you can see there's quite an extensive list on my screen. So we get some text-based interfaces with some software, and then we get some direct integrations. And then finally, we also get some interfaces, which will mainly entail some plugins between the software in that sense. Okay, so unfortunately, as you can see, Flownex is not as of yet an existing or built-in integration or interface, hence why we needed to make use of the common text-based interface or the Python interface. So you can make use of them interchangeably depending on which one you feel more comfortable with. So I don't want to spend too much time on how the interface works, but I'd quickly like to just give you a high-level workflow in case you may be interested to do this in the future. So when you make use of the common text-based interface, you make use of input and output text or ASCII files. So within OptiSlang, you'll use a solver wizard to set this up. So basically, you'll have your input file with all your input parameters in this input file. And then OptiSlang will take this input file, vary the input values, send it through the Flownex solver in batch mode, and then write the outputs for all the variables that it has selected. Okay, so that is how the text-based interface will work. And then, of course, we have the Python interface as well. It works on a very similar principle to the text-based interface, except that you don't actually need to make use of these text files, which could be or can be a bit tedious if you have to go manually set up your input and output files. So what makes the Python interface nice is you can go and directly plug in your input parameters into the code. So if you are quite well-versed and very comfortable in the Python scripting world, then you'll be easily be able to set up this workflow as well. It's also highly customizable, so you can maybe add some additional GUI interfaces for defining your input parameters, etc. And then again, if you're well versed in Python, it should be quite easy to set up. If you're not, there are some very detailed comments in the script that will help you to set up the workflow as well. All right, then the next thing I'd just like to focus on within the OptiSlang capability list is just the variation analysis and the multi-objective optimization that we can do within OptiSlang. So there are a number of other capabilities available, like robustness analysis and reliability analysis. But for the purposes of this webinar, we'll just be focusing specifically on multi-objective optimization, since we have two competing objectives that we would like to optimize for. Okay, so we started off by integrating our solver into OptiSlang by using Python or the Common Text-Based Interface. We then did a sensitivity analysis. So OptiSlang will automatically select the subspace and values of your variables for you based on the sampling method that you have defined. So if you are familiar with some sampling methods, some of you might know that there's one called the Latin hypercube sampling method. In this case, we made use of the advanced LHS method since it is well suited for models with a high number of variables. Okay, so from this, OptiSlang will then generate a set of responses, and then it will go further for you to understand your design a bit better. So it will take these responses and then generate something called a meta model of optimal prognosis, or a MOP, which is kind of like a reduced order model. But what makes it unique is that it also provides you with a metric called the coefficient of prognosis, or the COP, which is basically a measure of the forecast quality of your model. So traditional ROMs or meta models will typically give you a coefficient of determination, which will basically just give you a measure of the goodness of fit of your model. But what makes this unique is that it also gives you this forecasting quality, giving you ease or just more confidence that your model is accurate enough to use for downstream optimization. Okay, so in our case, we also made use of an adaptive meta model of prognosis. So it's basically the same, but what it will do is it will actually go and locally refine your subspace in order to increase the quality of your model, and it will iterate until it has reached that desired quality. Okay, so once you have generated this meta model and you know the quality is sufficient, then we go to our pre-optimization step. Okay, so from here, we will use our meta model for optimization, enabling us to send thousands of design points in a matter of minutes in order to generate our optimal design space. Okay, so for multi-objective optimization, of course, as well, you'll be able to extract your Pareto plots from OptiSlang. So we'll cover that a bit further on, but basically your Pareto frontier or your Pareto plot is just an indication of all your optimal solutions. Okay, and then during this process, it will also send the best designs that it has selected through to a verification system, where it basically sends the design points through to the Flownex solver in order to verify the meta model response. Okay, then after this, you can do final optimization. So if you have your Pareto plots, you'll obviously need to go and select the best design. We didn't include that in this webinar, but for this, you'll need extensive knowledge of your system, and you'll perhaps need to start incorporating some more constraints on your objectives in terms of available budget or required power output, etc. So for this, it will be more system-based in order to make that decision. Okay, just so to reiterate, the input parameters that we'll be feeding into our interface are the shaft speed, as Riani has mentioned. We also have the diameter of the preheater heat exchanger tubes, the fluid path length of those tubes as well, and then finally the mass flow of the cooler and the heater as well. So we've also indicated the ranges on the left. So these ranges you have to feed into OptiSlang for it to be able to select variables or values within those ranges. Okay, and then finally it will then calculate the responses for us and then generate the Pareto plot in order for us to evaluate our best designs. Okay, so just jumping into the results that we've achieved. So this is the response for the excess power or the power generated. And on the left, you can see the adaptive meta model iterating over a number of iterations, locally refining the model. You can see on the bottom left in order to achieve this desired quality. So it took about 10 iterations to achieve the COP of 83%. So that should be sufficient for optimization. In some cases, they do also require 90% if your model is a bit more sensitive. Okay, what I'd also just like to point out is in your meter model, it will also give you an indication of which parameters are the most significant or which parameters your responses are most sensitive to. And then that is what it will plot your response against. So in this case, you can see that the parameters or input parameters that played the biggest role are the shaft speed as well as the diameter of the heat exchanger tubes. But I'll give you some more information on the slides to come. Here is just an annual plot to show you exactly where the meter model decided to go, or Optislang decided to insert some additional design points in order to increase the quality. So this is just a nice visual representation of exactly where it was refined. Okay, then for the excess power response still, we can plot our individual coefficient of prognosis values for each input parameter. And basically what this means is it just shows the significance again of this input parameter, as I've mentioned in this case being the diameter of the heat exchanger tubes as well as the shaft speed. So in this case, if you maybe want to go make your model more efficient, you can get rid of your lower or less significant input parameters, making your meter model a lot faster and a lot more efficient while still being accurate. Okay, then you can also plot things among many others like a residual plot, and this kind of just gives you an indication of your approximated values against your actual data values, and it will give you some error bounds as well, indicating how well your model fits through the regression points, as well as how good the forecast quality is as well. Okay, so here is the response for the lifecycle cost. In this case, the lifecycle cost that was computed by the Flownex engineer is mainly for the turbine itself and some of the downstream piping. So it's not the cost of the complete power cycle. I just don't want you to think that it's a super cheap power cycle. Okay, so basically you can see, as expected, the shaft speed by far plays the biggest role in this life cycle cost of the turbine, which is as expected. Okay, so as you can see, we have these two competing multi-objectives where the shaft speed plays a role. So when you increase the shaft speed, you generate more power, but you also increase the life cycle cost. So where does your optimal point lie? Okay, so from this, we go over to our multi-objective optimization that we can do within OptiSlang. So we generate this workflow again from a automated wizard. So you don't have to manually set up this whole workflow. It's very easy to do in OptiSlang. So you have your AMOP or your sensitivity analysis, which will be followed by your optimization algorithm. In this case, it was the evolutionary algorithm that was selected by OptiSlang. This is a nature-inspired optimization algorithm and is based on evolution theories. It's very sophisticated, of course, so if you want to maybe see some of the maths behind it, we can also always send you some more information on that. And then as you can see, it also takes some of the best designs on the right. It will filter those best designs, send it through the validator system, as I've mentioned before. So in this case, it sends those best designs through to the Flownex solver to compare the response generated by the solver compared to the meter model. And then finally, it also just adds those points for post-processing. Okay, so just looking at our optimization response plots that we achieved, as you can see, on the right, it highlights all the Pareto optimal solutions. So we'll also still get to the Pareto plots. And just for a recap for those who may not be aware, so your Pareto optimal solutions just mean that you cannot increase the one objective without deteriorating the other one. So there's no other design that can dominate this design. So all of these are optimal depending on the constraints on your objectives, as I've mentioned before. Okay, so you can see that the optimal subspace is consistent for the lifecycle cost as well. So our optimal subspace is highlighted in those red points, and these then correspond with the red line you can see here on this Pareto plot. So the curved line at the very bottom depicts all your Pareto optimal solutions, and then there's very faint green lines over here that you can see. These depict your best designs that were sent through to the validator system through Flownex. So basically, it will take some of these optimal designs, send it through the Flownex solver, as I've mentioned, and then you can see that there is some error between the two responses. But again, you can still use either to get your most optimal points. Okay, so if you get a meta model with a higher coefficient of prognosis, then this error margin will decrease as well. But in this case, it's still sufficient to be able to select a optimal design. Okay, so just as an example, I selected a design, which was design number 462, which I thought was quite suitable design. And in this case, what is nice that it spits out the exact input parameters that will achieve this output. So here you can see that it gives you all the input parameters as the results, and then it also gives you a comparison between the calculated excess and life cycle, excess power and life cycle cost. So that is calculated through the Flownex solver. And then it also gives you the result of the meta model as well. And then you can see there is about a 5% error between the two. And as I've mentioned previously, if you actually go and increase your coefficient of prognosis, then you'll be able to reduce this error if need be. Okay, but in this case, we felt it was quite sufficient in order for us to evaluate our best designs. And then, of course, the next step after this would have been to go and evaluate your best designs with constraints to choose the final best one. Okay, so just to conclude, I'm going to just go through these 3 points, but basically the interface between the Flownex and the OptiSlang software will allow us to use sophisticated variation and optimization algorithms to be able to optimize fluid systems within Flownex. And then the adaptive meta models that we can use in OptiSlang, which are unique to OptiSlang, make it very easy and very efficient to predict the behavior of our complex system and to optimize based on this meta model. And then finally, it is very easy and very quick to set up a multi-objective optimization problem within OptiSlang using this interface based on the Pareto frontier. You don't actually need an extensive background or extensive knowledge on optimization to be able to set up these workflows. All right, and that brings us to the end. If there are any questions, please feel free to ask us. We'll be here. Okay, thank you. Okay, so are there any questions? Laura, I don't know if there are any questions so far. Oh, there's something in the chat. Okay, let's see. Okay, so there's a question from Valerie. She says, hey, I have a question. What are the advantages of using OptiSlang compared to embedded Flownex optimization? Does OptiSlang work quickly or more stable? So Riani, you may also need to give some input here, but as far as I'm aware, there's a lot more capability built into OptiSlang, especially with regards to measuring the quality of your optimization and having the capability to trade off between the multi-objectives, as far as I'm aware.
Yeah, so first off, thank you very much for your question, Valerie. Of course, you can run this optimization study in Flownex with multiple differentials and stuff like that. The main advantages, I would say, is the visualization and the ability to add more variables. And as you've mentioned, John, yeah.
Yes, yeah. So as Riani says, with OptiSlang, you can have up to 20, 30 variables even. We only demonstrated having 5 at this stage, but you can have many more. And then on top of that, of course, you can also do reliability analysis and robustness analysis of your best selected designs as well. Okay, does that answer your question, Valerie? Okay, fantastic. Are there any other questions? Okay, okay, there's someone typing. You guys are also welcome to unmute yourselves and ask a question if you don't want to type. It's also fun.
Johnny, let's just give a few minutes to see if there's any further questions.
Yeah, no problem. I see there are 2 people still typing.
Okay. Yeah, maybe they prefer to type and then we can answer.
Yeah, that's fine. All right, no problem.
No, I prefer talking to typing.
Okay.
From Wild. When you were selecting that particular point on the Pareto front, what sort of criteria do you use to select that particular point on the Pareto front? Because
Yes, so that is a good question, and that's unfortunately where from OptiSlang's point of view, from generating your Pareto plot, taking it further, as I've mentioned, requires extensive knowledge of the system. So in this case, I just for demonstration selected a best design, but that would be based on the constraints on your objectives. So in this case, we have not considered that yet, but that would be things like your budget range is within this and this value, and your required power generated will be this value. So then as you use these constraints, you can narrow down your best designs. And then there are also other methods of using like weighting factors between the two that I still need to look into a bit further so that you can, so that can aid you in selecting the best design as well. But doing or selecting a best design from your Pareto frontier is quite a sophisticated and complex process, as I understand. Also something that I'm still becoming familiar with at this stage.
Yeah, that makes perfect sense. Thanks very much. Yeah.
All right, no problem, Simon. Okay, I see Bernie still also typing. Okay, so Bernie's question is, thank you for your question. Does OptiSlang give values for the confidence intervals ranges of the meter model? Bernie, can you just please clarify what you mean with the intervals or ranges?
Yeah, what I mean is you've fitted now a surface through data points. So
Yes.
there's some fit error. I mean, if you think
Yes.
simplistically of fitting say a quadratic curve through a couple of points, you get plus minus error for your
Yes.
confidence interval, 95% confidence interval. Then you get how large is that confidence interval, because it gives you kind of a buffer area for how accurate is your model.
Yes, so I don't know if OptiSlang makes use of an exact term called the confidence interval, but it does give you a number of different metrics to be able to evaluate the quality of your meter model. One of which, as I've mentioned before, is your coefficient of prognosis, but it also can give you your residual plots, which will give you your error bounds based on inputs, and it can also give you your coefficient of determination, and there are really many other metrics that you can extract from OptiSlang. Perhaps if you're interested, Badly, we could, I can send you through some of that info afterwards that is available in order to evaluate that confidence level that you're talking about.
Yeah, thanks. It was, I was just wondering that it doesn't just stay with visuals. You sometimes need to actually work with actual numbers. Yeah,
no, you'll be able to extract even the tabular values, and you'll be able to calculate like your root mean square error. It also will give you metrics like that as well. So what I've shown you really is only the tip of the iceberg of what you can do with OptiSlang, if that makes sense.
Okay, thank you very much.
No problem, Benny. Okay, yeah. Any other questions, guys?
Yeah, me again. Sorry, Simon. Leaf again.
Yeah.
Just to be clear, so when you're basically scooting through the thousands of design permutations, what you're doing there is you're interrogating the response surface that's been generated from the Flownex model rather than running Flownex simulations. Yeah.
100%. Yes, exactly. Yep, so luckily with Flownex, OptiSlang and Flownex work quite well together because Flownex solves so quickly. So even optimizing on the Flownex solver would be feasible because it solves so fast. But using this meter model for optimization makes it even like more. It just increases by a factor of 10, at least, I would say, in speed to be able to optimize on that meter model. But again, if you do so, it is very important to make sure that your meter model quality is sufficient and for optimization, and that it's also required for you to verify your meter model with some solver calls from Flownex as well.
Yeah, and if you found that your meta model was not of sufficient quality, what would you do? Would you go back and sort of review your sort of lattice hypercube points or something?
Yeah, so you can review your sampling methods, and of course, if you increase your number of sample points, your quality will also increase generally. So they generally say that you need to have at least twice the number of your number of sample points must be twice the number of variables that you have. But in most cases, you need much, much more than that. So you can maybe even go play around and start with like 10 points and then 20 and 30, and you'll see how your quality will increase. But it's not always the case. Sometimes it is necessary to go and look at your sampling method specifically. And the adaptive meta model especially is also a very good way of increasing the quality that Flownex will do, not Flownex, that OptiSlang will do for you. So that's why I use the adaptive model, because in this case, increasing the quality, increasing the sampling points didn't necessarily increase the quality. So I had to play around with the adaptive model in order to achieve the required quality.
Thank you, that's really helpful, thanks.
All right, no problem, Simon. Then I see another question from Barney. Can something similar be done for CFD models? So yes, if you're referring to the optimization part, you can definitely interface OptiSlang with Fluent or CFX probably through Workbench. So you'll be able to do exactly the same thing. You probably won't even need to make use of the text-based or the Python interface because there's a direct integration already built between OptiSlang and Workbench. So that will be probably a bit easier to set up as well. Okay, and then you also said meta models used for optimization would make more sense when your model solves for the response. Yes, exactly. So for Flownex, as I've mentioned, you could optimize with the solver because it solves so fast. But if you are running something like a CFD analysis, which could take maybe hours or even days to solve, it makes sense to use a lot less design points and then optimize based on those. And that's where it becomes very critical to select the appropriate sampling methods and meta models, etc. And I hope that answers your questions, Barney.
Yes, thanks. I was just wondering because different software that I've seen that also does similar kind of response surface and optimization things actually does it for a CFD, and for that it actually blew my mind away that you can actually get something that's accurate enough, that's a simple formula that you can use and actually optimize using that.
Yes, yeah, that is the whole point of OptiSlang, is exactly that, is building those reduced auto models in order for you to use them downstream for all your reliability analysis, etc.
Thank you.
Okay, no problem, Benny. Okay, Laura, I don't know if there will be any other questions. So, yeah. Laura, are you still there? Maybe she's muted. I'm not sure. Okay. Otherwise, guys, if you don't have any other questions, then thank you for attending today. Please feel free to contact us if you have any further technical questions, or if you are interested in how this interface works. If you maybe want to set it up, we can assist you further. Also, if you have any further queries on specific Flownex capabilities or OptiSlang capabilities, yeah, please just pop us a mail and we'll assist you. Okay, thanks, guys.
Thank you very much.
Thank you. Thank you.
Okay, thanks a lot.
Thank you, John.
Bye.
Thank you. Okay.